We are almost done with the comparing different integration techniques, but what we want to do is get back to where we're at again. So let me just refocus you. We've developed lens space. So this is how I went about breaking up my problem into different sort of segments here. I think the ones that I've numbered 1, 2, 3, 4, I think they're very obvious. If you didn't see those, like you're going to have to program that technique, then you probably need to work on sort of figuring out how to decompose problems into simpler problems. This one probably is staring you in the face as well, and this one is too. But just realize that, I mean, while you were going through each one of these, you would have had to have done something like this for each one of those. And so hopefully, as you get more experience, you could see that a need for developing your own little program or little function that does this business here. And then what we're going to do in class, I believe, is we're going to develop a test function that's going to take all of this stuff that we've programmed and compile it into what I call, or what many people call, like the main program. So this is the thing that's you're going to pass in whatever your ends are, maybe 5, 10, 20, 50, 100. And then what your program is going to do is then pass those into the different functions and then find out what the results are and report them on something that we know the answer to. So we'll know what the error is for each one of those. And that's how we want to go about doing it. All right, so let's jump into the programming piece and start doing that. So sort of where we left off last time, if you remember, we did lens space. We did a left-hand rule where we returned the area. And then we saw that it was getting closer and closer. And I actually did the calculation. It is actually 41 1/3. So that's a good thing that it gave us what we were looking for. And now let's go ahead and do Simpson's rule. So this one might be a little difficult. And it's not that difficult. I mean, if you just look and see at the formula, so and just think about each one of those intervals you have to do that for, it's fine. So we're going to pass in f, a, b, and n. And then same thing. So matter of fact, I'm just going to copy all this. Let me just copy this. Control C, Control V, and then you got to line this stuff up. So I got to line X list back up. Delta X is the same, area is the same, and then when I get into here, it's the same because am I using the last number? I am not. So all of this becomes the same. So Y0 is not this one, is not f of x. Y0 is x underscore list is it I? Yeah. I got to do I comma. So I got to enumerate this. So I comma enumerate. So we want to enumerate. I need the index now. The reason why I need the index is because I need the ith one and I need the I plus one and instead of just going into X and then trying to find the index using X. I mean, we could go back and indirectly find this index, but we can just get it like this. So we're going to enumerate this guy and it'll give us the I. So X list I and then Y, oops. And we want Y1 to be the guy in the middle, or X or YM if you will. So we're just going to simply take the ith one and I'm going to add the list of I plus 1. And then I need another parenthesis here so that I can divide that sucker by 2. And that's what Y1 is going to be equal to. And then Y2 is going to be, so what that's giving you the left part of the interval. This is giving you the middle part of the interval. And then we want the right side of the interval. So Y2, or the interval. And so that'll be f of x underscore list I plus 1. Okay. So I have all of the information I think that I need, and so I'm just going to simply add, I can just put it right down there. So we know it's this y0 plus, and I'll put the space in there, 4 times y1 plus y2 times delta x. And somewhere I got to divide by 6, right? And then I can multiply by delta x. And then times y. I don't need y0. Y0 was basically this, was the height. Our height is different now. Our height depends, is that polynomial, is the integral of that polynomial that goes through those 3 points. Remember when we used SimPy in order to find out what this equation was. And so that's going to be the equation for each one of them. So let's F9. Let's find out what this thing is saying. So F, so we already have an F. I'll do Simpsons. And the cool thing about Simpsons, for a quadratic formula, think about it for a second before I even put this in here. We should get the exact answer. And think about why that's true. I can get the answer with 2. Because it's going to match the left and right. Well, let's see. Yeah. So it gives us the exact answer, because what it does, what Simpsons does, is it turns it into a quadratic function, which is exactly what we want. We want a quadratic function for that thing. So that's how I knew we were going to get the right answer for it. And you can put in 10 if you want, and you get the same. I mean, you get this rounding error out here. Okay, that is it for this lesson. So the next thing that we have to do, let me pull up one note. The next, so I've done lens space already. I've done this one. Bring this code in with you in the class. Bring your work in for your right hand rule and your trapezoid. Make sure that they're giving you sort of the same, about the same numbers that we've been getting for, I get, what is it, 41 1/3. That if these are giving you about the same thing, and the right hand rule should be coming at it from above. Left hand rule for a quadratic going from 1 to 5 should be coming at it from the left hand side. In other words, from smaller. Let's see. No, hold on. It should be high, right? I think. Let me get that sucker. 41. Here, left hand rule 1 4. So it was, yeah, it was smaller. So it's coming at it from yes, okay. So it's a left-hand rule, so it's underneath the curve, and the right-hand rule should be on top of the curve. So you should be coming at it from the different side. And then trapezoid is going to be, should be better than the left and the right-hand rules, but certainly not as good as Simpsons. All right, that's all we got. Hopefully everyone got something out of it. I will see you next time.